This is Colin Selleck of Binghamton University. This video lecture is from the book Statics by R.C. Hibbeler. It's for the course ME273 Statics. And today we're covering 3.1, Condition for the Equilibrium of a Particle, 3.2, the Free Body Diagram, and 3.3, Coplanar Force Systems. After today, you will be able to draw a free body diagram and apply the equations of motion to solve a 2D problem. We'll go over some applications. We'll talk about free body diagrams, discuss the equations of equilibrium, look at springs and pulleys, and then we'll do some problem solving. So this crane is lifting a load. To decide if the straps holding the load to the crane hook will fail, you will need to know the forces in the straps. And today we're going to find out how to do that. Here's a spool, and it has some weight. Now, how would you find the forces in the cables AB and AC? And if you're designing the spreader bar that goes between B and C, how would you determine the forces to make sure that the rigging doesn't fail? And lastly, we have a tanker ship here, a boat, and it has a towing pendant, this DB and CB. So what are those forces in those bridle cables? And what size of cable must you use? Now, if a particle is subjected to a system of coplanar forces that lie in the XY plane, so coplanar means it's all in one plane or a sheet of paper. And we use the XY plane here. You can resolve each force into its X and Y components. And for equilibrium to be maintained, the summation of forces is equal to 0. Which also means summation of forces in the X, in the I direction, plus summation of forces in the Y, in the J direction is equal to 0. Now these two equations, there are two equations in a 2D vector equation, so they can be solved for at most two unknowns. And generally those unknowns are either the magnitude of the force or perhaps the direction of the force vector. Now when applying each of the two equations of equilibrium, we must account for the sense of direction of any component by using an algebraic sign which corresponds to the arrowhead direction of the component along the X or Y axes. It's important to note that if a force has an unknown magnitude, for instance in this case here F, then the arrowhead sense of the force on the free body diagram can be assumed. That means you can draw F in this direction or in the opposite direction. Then if the solution reveals a negative scalar, this indicates that the sense of the force is opposite to that was assumed. For example, consider the free body diagram of this particle right here, which is subjected to two forces, 10 newtons and an unknown force F. Here we assume that F is to the right, that is in the positive X direction. If you apply the equation of equilibrium, summation of forces in the X is equal to 0, you'll get F plus 10 equals 0, or F equals minus 10 newtons. So what that means is, since it came out negative, it means that this force vector F is actually in the opposite direction that you assumed it to be. So a particle is said to be in equilibrium if it remains at rest, if originally at rest, or has a constant velocity if originally in motion. Most often, however, the term equilibrium, or more specifically static equilibrium, is used to describe an object at rest. To maintain equilibrium, it is necessary to satisfy Newton's first law of motion, which requires the resultant force acting on a particle to be equal to 0. This condition is stated by the equation of equilibrium. Summation of forces as a vector is equal to 0. Now, summation of F is the sum of all the forces acting on the particle. Not only is this equation necessary for equilibrium, it is also a sufficient condition. This follows from Newton's second law of motion, which can be written summation of forces is equal to mass times acceleration. Now this, in the case of statics, we know that has to be equal to 0, which means that since the mass is not 0, that the acceleration is 0. So in the case of statics, summation of forces is equal to 0. This equation we'll use in dynamics. Now, before presenting a formal procedure as to how to draw a free body diagram, let's look at some 3 types of supports often encountered in particle equilibrium problems. The first is a spring. In a linearly elastic spring or cord of undeformed length L0, that means the spring is not under load. What is its length? That would be L0. So if that spring is used to support a particle, the length of the spring will change in direct proportion to the force F acting on it. A characteristic that defines the elasticity of a spring is the spring constant, or stiffness, sometimes it's called, K. The magnitude of the force exerted on a linearly elastic spring, which has a stiffness K and is deformed, elongated, or compressed, a distance S, which is equal to the length of the spring minus its unstretched length or unloaded length. So that force in the spring is equal to the spring constant times S. If S is positive, which causes an elongation, then the force F must pull on the spring. Whereas if S is negative, causing a shortening, then F must push on the spring. For example, if the spring in figure 3a has an unstretched length of 0.8 meters and a stiffness of K of 500 newtons per meter, note the units on that spring constant, newtons per meter or pounds per foot. And now if it's stretched to a length of L is equal to 1 meter, then S is equal to 1 minus 0.8, right? And that would be in meters, which is 0.2 meters. So the force F is equal to K, which in our case is 500, times S in meters, which is 0.2. So the force is 100 newtons. The next thing we'll look at is cables and pulleys. Now, unless otherwise stated throughout this course, except in section 7.4, which we won't cover anyway, all cables or cords will be assumed to have negligible weight and they cannot stretch. Also, a cable can only support a tension or a pulling force, and this force always acts in the direction of the cable. In chapter 5, we'll show that the tension force developed in a continuous cable which passes over a frictionless pulley must have a constant magnitude to keep the cable in equilibrium. Hence, for any angle theta, the cable is subjected to a constant tension T throughout its entire length. So what we're saying is that the tension on both sides of a frictionless pulley are equal. The next thing we'll look at is smooth contact. Now, if an object rests on a smooth surface, like in this case on this 30-degree inclined plane, then the surface will exert a force on the object that is normal to the surface at the point of contact. So here's an example, and we see that we put the normal force normal to or perpendicular to the plane. So it's at 30 degrees from the negative y-axis. In addition to this normal force N, the cylinder is also subjected to its weight and the tension T in the cord. Since these three forces are concurrent at the center of the cylinder, we can use the equations of equilibrium to this particle. Let's talk briefly about what a particle is. A particle has negligible size, but it has a mass, so we just treat it as a point. Now, eventually we'll get into something called a rigid body, where the size of the body does matter, but right now we're just talking about particles. So again, particles have a mass, but very small size, and we just assume it is a point. Now, to apply the equations of equilibrium, we must account for all the known and unknown forces which act on the particle. To apply the equations of equilibrium, we must account for all the forces and unknown forces which act on the particle. The best way to do this is to think of the particle as isolated and free from its surroundings. A drawing that shows the particle with all the forces that act on it is called a free body diagram. Free body diagrams are one of the most important things for you to know how to draw and use for statics and other subjects such as dynamics and strength of materials. So what is a free body diagram? It's a drawing that shows all external forces acting on the particle. And we can also say it's acting on the rigid body, but we'll get to that later on in the course. Why do you want to do it? It's key. That's why you must be able to write the equations of equilibrium and use those to solve for the unknowns, which are usually forces or angles. So how do you draw a free body diagram? Since we must account for all the forces acting on the particle when applying the equations of equilibrium, the importance of first drawing a free body diagram cannot be overemphasized. To construct a free body diagram, follow these steps. First, you draw the outline shaped. Imagine the particle to be isolated or cut free from its surroundings. This requires removing all the supports and drawing the particle's outline shaped. So in this case, we're going to isolate particle A by drawing a circle around it. And then we'll put all the forces acting on that particle and their directions. So this one's in the negative x, this one's in the negative y, and this is 30 degrees in the first quadrant. Show all the forces. These forces can be active forces, which tend to set the particle in motion, or they can be reactive forces, which are the result of the constraints or supports that tend to prevent motion. To account for all these forces, it may be helpful to trace around the particle boundary, carefully noting each force acting on it. Identify each force. The forces that are known should be labeled with their proper magnitudes and directions, as you see here. Letters are used to represent the magnitude and direction of forces that are unknown. In this case, F sub D and F sub B. So this is the free body diagram of this system right here, and it's replicated right here. And since particle A is at equilibrium, the net force at A is 0. So we can write that FB plus FD plus FC, those are all vectors, is equal to 0. You can also write summation of forces is equal to 0. Now if we're in Cartesian notation, it's the summation of forces in the x and the I direction plus summation of forces in the y and the j direction plus summation of forces in the z in the k direction is equal to 0. That's a vector equation. You can also write scalar equations. You can say summation of forces is equal in the x is equal to 0, summation of forces in the y is equal to 0, and summation of forces in the z is equal to 0. So these are scalar equations. So let's solve this problem. Here we have a cylinder of mass 40 kilograms. Now that's the mass, it's not the weight. The weight, to get the weight from the mass, you always multiply by acceleration due to gravity. So in this case, the weight is 40 times 9.81, or 392.4 newtons, which you see here. So let's write the scalar equations of motion. So let's first let's sum forces in the x. So we have FD, but it's pointing to the left, so it's negative. FC doesn't have a component in the x direction. FB does. It's in the first quadrant, so it is plus FB times the cosine of 30. That's equal to 0. Now we sum forces in the y. We have the component of FB in the y direction. It's positive. FB times sine of 30. And we have the weight, which is negatives pointing down, so minus 392.4. It's equal to 0. So from the second equation right here, we can get that FB is equal to 785 newtons. And then we plug that in right here and solve for FD, and FD comes out to be 680 newtons. Now they both came out positive, so that means we assumed the sense of the direction correctly. So FD is pointing to the left, as you see here, and FB is in the first quadrant, as you see here. So let's do some examples. Here we have a box that weighs 550 pounds and has the geometry as shown. Find the forces in AB and AC. So our plan is to draw a free body diagram for point A. We're going to draw a circle around it and see which forces cross into that circle. And then we'll apply the equations of equilibrium to solve for the forces in ropes AB and AC. So first let's do the free body diagram. So I have this point A, and there is a force in the AC cable, which I'm going to call F sub C, and it's on a 3-4-5 triangle. Then we have the weight to the box. Now this one is the weight, 550 pounds is a force. And then we have the tension in cable AB, and it's in the second quadrant, 30 degrees from the negative x-axis. So you also have to always put a coordinate system on your free body diagrams. And this I'm going to call F sub B. So here's our free body diagram. There's only two unknowns, right? We know F sub B's direction is at 30 degrees. We know FC's directions on a 3-4-5 triangle. So the only unknowns are the magnitude of FC and FB. And remember, in a two-dimensional system, you can solve for at most two unknowns. So we have two unknowns, so we should be able to solve this. So first, let's sum forces in the x. So FB's in the second quadrant, so its x component is negative, and it's FB times cosine of 30. The 550 pounds has no component in the x, but the FC force does. It's in the first quadrant on a 3-4-5 triangle, so it is plus F sub C. I think I drew this triangle wrong. It's actually a 3 high, 4 wide triangle. So the component of FC in the x direction is 4/5. So there's one equation. Now let's sum forces in the y. And we have the component of FC in the y direction. It's positive, and it's times 3/5. And then we have the component of FB in the y direction. It's also positive, and it's times the sine of 30. And then we have finally the weight, minus 550. All that's equal to 0. We have two equations, two unknowns. You're welcome to use your calculator to solve these simultaneous equations. You can do them by hand. I like to use an online resource at wolfram.com. But anyway, when you solve these simultaneously, we'll get F sub B is 478 pounds, and FC is 518 pounds. And that's the solution to our problem. Let's do another example. Now we have two masses. We're told the mass of cylinder C is 40 kilograms. Find the tensions in the cable DE, EA, and EB. So we're going to draw a free body diagram of point E and then apply the equations of equilibrium to solve for the forces in the cables. So first, let's draw the free body diagram. We're going to isolate particle E. So here's E. There's a force directed to the left. I'm going to call that T sub ED. There is the force in the cable EA, which I'm going to call T sub EA. And then we have this cable at 30 degrees in the first quadrant. So I'm going to call that one T sub EB. Now we have three unknowns here, so something's got to, we need another equation, we need something else. Well, remember, frictionless pulleys, the tension on both sides of the pulley is equal. So if you draw a free body diagram of that point B, right, you'll get the weight, which is 40 times 9.81, and you'll get, this tension in EB. Since this is a frictionless pulley, the tension in EB must be equal to the weight of cylinder C. Okay, so now we know TEB, it's 40 times 9.81. So now we can sum forces in X and Y and solve. Now we only have two unknowns, right? This one and this one. So let's sum forces in the X direction first. So TED, that's in the negative X direction. TEA doesn't have a force in the X direction. TEB does, and it's positive, so this will be plus 40 times 9.81. That's the weight of this cylinder, times the cosine of 30. So from that, you can solve for TED, and that's equal to 340 newtons. Came out positive, so that means it is indeed directed to the left. Sum forces in the Y. And we'll get, now we have the component of TEB in the Y direction, and that's going to be times the sine of 30, so it's 40 times 9.81 times the sine of 30. And that's positive, it's pointing up. And then the other force in the Y direction is T sub EA, and that's negative T sub EA. So we can solve for T sub EA and get 196 newtons. And again, it came out positive, so that means that we assumed the direction correctly. So this is pointing down. So let's do another problem. This one's a little more complicated. We know the mass of the lamp is 20 kilograms. Find the force in each cable. So we have cable DF, DE, DC, AC, and BC. And we know all the directions of those forces, but that still means we have, 1, 2, 3. We have at least 4 unknowns, maybe 5 if you count DF. So what we're going to do is two-step approach. First, we're going to draw a free body diagram of point D, and then we'll solve for the unknowns FCD and FDE, these two. The tension in DF is 20 times 9.81. We know that because we know the mass of the lamp. And then when we finish solving for those, we'll repeat the process, but this time we'll do it at point C. In that case, we will know what TCD is because we will have solved for it earlier in the previous free body diagram. So now we just have two unknowns, so we should be able to solve this problem. So let's first draw the free body diagram. Let's do point D. So this is point D. So we have D, we have the tension in DE. That's at 30 degrees. We have the weight of the lamp. The lamp is 20 kilograms, so multiply it by the acceleration due to gravity. So it's 20 times 9.81, and that would be in newtons. And then finally we have FCD, or TCD. Okay, two unknowns, the magnitude of TCD and the magnitude of TDE. We know the directions of those vectors, so we should be able to solve this. So let's first, with some forces in the y first, and we'll get the component of TDE in the y direction. I've got to put my coordinate system on here, x, y. So summation of forces in the y is tension in cable TDE times the sine of 30. And that's pointing up, so it's positive. And then we have subtracted off the weight, 20 times 9.81. And from this, we can solve for TDE, 392 newtons. Now let's sum forces in the x direction. This is equal to 0. X direction, so we have the component of TDE in the x direction. It's positive, right? First quadrant, so TDE times cosine of 30, and then the only other force in the x direction is TCD, and it's negative. Since we just solved for TDE, we can solve for TCD and get that TCD is 340 newtons. Great, so now we know the tension in cable CD and the tension in cable DE. So now let's move on and draw the free body diagram at point C. So draw a circle around it and draw an outline of its shape. And then we have the tension in AC, and that's on a 3, 4, 5 triangle, right? And then we have the tension in CB, which is at 45 degrees from the negative x-axis. And then the final thing we have is TCD. But we already solved for that earlier, right? We got TCD is 340 newtons, so we know that. You just have to draw it in the right direction. You have to draw it to the left, to the right this time. That's 340 newtons, right? Because if it's pointing this way in the free body diagram of D, it has to point the opposite direction in the free body diagram of C, and that's very important to do it that way. If you drew 340 newtons to the left here, you would get the incorrect answer. In fact, you wouldn't get an answer at all because there's no forces in the x direction in that case. Okay, so anyway, let's sum forces in the x and set that equal to 0. So in the x direction, we have the 340 newton tension in cable CD. Then we have minus TCB because it's in the third quadrant times the cosine of 45. And then TAC, the x component is also negative, so it's minus TAC times 3/5. So there's one equation, two unknowns. So let's get the other equation. Summation of forces in the y is equal to 0. So in the y direction we have TAC is positive, it's in the second quadrant, so T sub AC times 4/5. And then TCB, it's in the third quadrant, so its y component's negative TCB times the sine of 45. And the 340 Newton force is all in the x direction, so it doesn't come into play in the y direction. So now we have two equations and two unknowns, and when you solve for them, we get the tension in BC is 275 newtons, and the tension in AC is 243 newtons. Okay, this concludes the lecture on section 3.1, condition for the equilibrium of a particle, 3.2, the free body diagram, and 3.3, coplanar force systems. The next video in this series is section 3.4, three-dimensional force systems. See you in cyberspace.